Hello everyone, my name is Soumya Revatkar and my today's presentation topic is Introduction to Thermogravimetric Analysis. Thermogravimetric analysis is an analytical technique used to measure the change in the mass of the substance as a function of temperature or time under the controlled atmosphere. It is widely employed in material science, chemistry, and polymer industries to study thermal stability, composition, decomposition characteristics of material. The weight changes are recorded as a temperature increase or decrease, providing insight into physical and chemical phenomena like degradation, decomposition, and oxidation. There are three types of TGA system: top loading TGA, bottom loading TGA, and dual balance TGA. In top loading TGA, the sample is placed in a pan suspended from balance located from the furnace. It is suitable for small and light sample and it offers high sensitivity and rapid heating. In bottom loading TGA, the sample is placed on a platform or pan located inside the furnace. The balance is positioned below the furnace and it is commonly used in high temperature application due to improved thermal insulation. Third one is dual balance TGA system. It features two balance systems, one for the sample and another for the reference material. It provides simultaneous measurement, enhancing precision by compensating for environmental fluctuations. It commonly used in advanced research application. Instrumental requirements for TGA. First is sample mass. Sample mass of around 2 to 50 mg is used to ensure the accurate result as larger sample may cause uneven heating or incomplete degradation. Second is pan sample material. High temperature resistance material like platinum or ceramic are commonly used to withstand heating cycles and maintain inertness, minimizing interference with the sample. Third is heating rate. The standard heating rate of 20 degrees Celsius per minute is often employed, balancing between analysis speed and resolution of thermal events. Temperature range. Temperature range of TGA system is 1000 degrees Celsius to 1200 degrees Celsius. Working principle of TGA. A small amount of sample is placed in a TGA instrument. The instrument heats the sample at a controlled rate of 20 degrees Celsius per minute or it is maintained at specific temperature. Changes in the sample mass are continuously measured as a function of temperature or time. Mass changes occur due to the processes such as moisture loss, decomposition, oxidation, or reduction. Generally, in polystyrene, the thermal decomposition occurs between 400 to 500 degrees Celsius, and in this analysis, we get the thermogram as our output. The first stage in TGA requires meticulous sample preparation. A small quantity of material of around 5 to 20 mg is placed in a sample holder, ensuring it is evenly distributed to achieve the uniform heating. Proper sample preparation is essential to avoid inaccuracies in the weight loss measurements. An uneven sample can result in non-uniform heating leading to errors in the thermogram. Using the correct sample size and ensuring even distribution minimizes the variation in thermal exposure. Second step in the TGA is calibration and setting the temperature ramp content. Before analysis begins, the balance and furnace must be calibrated to eliminate potential instrument error. The temperature ramp rate, generally between 5 to 20 degrees Celsius per minute, is then configured. Calibration ensures the accuracy of weight reading and the furnace operates as intended. The ramp rate significantly impact the analysis. Higher rate may miss critical thermal events, while lower rate offer more detailed data but require more time. Third step is purging with inert gas. An inert gas such as nitrogen or argon is introduced into the furnace to eliminate oxygen and prevent unwanted reactions such as oxidation that might affect the weight measurement. Creating an inert atmosphere ensures that any weight changes observed are solely due to thermal decomposition rather than oxidation or combustion. This allows for a more accurate thermogram that reflects the material decomposition behavior under heat. Fourth step is heating and weight tracking. The sample is heated gradually according to a programmed temperature profile while the TGA instrument continuously measures the weight. As the temperature rises, the sample may experience weight loss due to processes like evaporation, decomposition, or other thermal transformation. A thermogram is generated showing weight changes as a function of temperature. Weight loss at specific temperature points signal distinct thermal events such as the release of water, organic compound, or structural breakdown. This real-time tracking is essential for analyzing thermal stability and material composition. Fifth step is decomposition and analysis of thermogram. The thermogram displays distinct stages of weight loss, each representing decomposition of specific components of the sample within a particular temperature range. Analyzing the thermogram reveals the decomposition temperature of various components. For instance, weight loss at lower temperature may signify water evaporation, while weight loss at higher temperature could indicate the breakdown of organic material or polymer. This analysis is a key to understand the material's composition and thermal behavior. This is the thermogram for polystyrene. So from this graph, you can see in the initial region, the stable mass indicating no thermal changes below 300 degrees Celsius, and in the decomposition region, there is mass loss between 300 to 500 degrees Celsius due to polymer chain evolution of volatile product, and in the final region, that is above 500 degrees Celsius, there is residual mass approaches to zero, indicating complete thermal degradation. The thermogram illustrates weight loss percentage as temperature rises. The curve shows three different regions. Stage 1 is initial weight loss at lower temperature that may indicate the solvent or moisture evaporation. In stage 2, there is major degradation stage around 400 to 500 degrees Celsius, and it may indicate the release of volatile products. The DTG curve derived from the TGA curve illustrates the rate of weight loss relative to temperature, emphasizing the point of most rapid change. The peak near 465 degrees Celsius represents the inflection point, indicating the maximum rate of weight loss. This marks temperature at which polystyrene undergoes its fastest decomposition, offering valuable information about its thermal stability and decomposition behavior. In essence, this curve reveals the thermal stability and decomposition property of polystyrene, with the primary decomposition occurring between 400 to 500 degrees Celsius, reaching its peak at 465 degrees Celsius. Applications of TGA in various sectors. So first is polymer and analysis. TGA is utilized to evaluate polymer stability, determine filler content, and study degradation behavior. It plays a key role in quality control and understanding thermal limitation. Second is pharmaceutical. TGA is employed to analyze raw material for quality assurance, access moisture content, and evaluate the stability of drugs at higher temperature. Third is environmental testing. TGA is used to study the decomposition of environmental samples under different atmospheric conditions such as inert or oxidative environment. Fourth is compositional analysis. TGA determines material composition by measuring the proportion of volatiles, fixed carbon and ash in substance like coal. There are some limitations of TGA. First is sensitivity. TGA may fail to identify minor thermal event in complex sample mixture. Second is atmosphere dependence. The result can be influenced by purge gas used, which affects decomposition and oxidation pattern. Third is sample size. Accurate analysis requires small sample size, typically 2 to 50 mg, as larger sample may lead to error due to uneven heating. So the conclusion is TGA delivers vital insight into material stability, composition, and thermal degradation, making it indispensable for product development and quality control across industries such as polymer, pharmaceutical, environmental science. It provides a detailed understanding of material behavior under heat, which is crucial for industries working with heat-sensitive substances. Precise analysis relies on optimizing factors like sample size, pan type, purge gas, and heating rate customized for each material.